One graph that's very special that comes up often is the complete graph on n vertices. This is a simple graph, simple meaning there are no loops and no multiple edges, on n vertices with every possible edge included. Here's an example of the graph K5. This is the complete graph on 5 vertices, as we can see here. Every vertex, of course, has degree 4 because it connects to every other vertex. So this is an example of a regular graph as well. So here's a simple question. How many edges does this graph have? How many edges are there on Kn in general? So every pair of edges, for every pair of vertices, there is an edge. So how many pairs of vertices? And of course, that's just n choose 2. So quite a lot, roughly n squared. Okay, there's another variation of this. We've been talking about directed graphs, and this is going to be a more exciting thing called a tournament. So a tournament, and let's try to make it stand out. What is a tournament? A tournament is just a way to direct the complete graph. Is a directed graph on Kn. So here's a question. How many tournaments are there on Kn? So as we think about that, let's look at this graph example that we have over here. Let's maybe pick purple, and let's take each of these n choose 2 edges. So there are 10 edges on this graph, and we'll choose a direction for each one. That's a tournament. So here we can choose this direction, and maybe we'll choose this direction. Up, up, over, 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 up, over, down. All right, I've put 10 arrows onto this graph. So I've directed all the edges, and now this is an example of a tournament. So how many tournaments are there on Kn? Well, for each edge, I made a choice. I could choose to orient it in one of 2 directions. So there are 2 choices per edge, and how many edges are there? Well, there are n choose 2 edges. So this is how many tournaments there are. 2 to the n choose 2 is the number of tournaments on n. And why do we call them tournaments? Well, because we can think of, if we played a round-robin tournament, a game where every pair of players has exactly 1 match and it's never a tie. That would be choosing an orientation. Say we direct from the winner to the loser. And that would tell us the outcome of the game. And so we can think of this graph over here as encoding the information in the outcome of a round-robin tournament. So let's make that specific with the following problem. So here's the problem I want to consider. There's a Connect 4 tournament, and every 2 players competes exactly once, and there are no ties. This is what tells us that it's a tournament in the graph theory sense. This is what a tournament is. Now, after the tournament, I'm going to have the players do the following. They're going to write down some names. They're going to write down the names of everyone they defeated and everyone defeated by someone they defeated. We want to prove that somebody's list contains all the names. At least one person has written down all of the names. Let's think about how that would work. Let's just take this and let's record the outcomes. So here, let's give these guys all numbers because it's just going to be a lot easier if I number them. So we'll go 1, 2, 3, 4, and 5. These are my players, 1, 2, 3, 4, and 5. So let's first go through and write down who did player number 1 defeat. If I look at this graph, I can see here's player 1. Player 1 defeated player 5 because let's say that, well, maybe we'll write this down. So we'll say that an edge going this way, this is the winner and this is the loser. Okay? So if we look here, we want to say, what are all the outgoing edges? Well, there's only one. So player 1 defeated player 5. Okay? Great. Who did player 2 defeat? So now we're looking at this one. Player 2 defeated player 1. And player 4 and player 5. So 1, 4, and 5. Who did player 3 defeat? Player 3, it looks like player 3 defeated 2, 1, and 4. Player 4 defeated player 1, and player 5 defeated player 4, player 3, and that's it. Okay, so this is my table of who defeated whom. And so you should check that the missing numbers here, for example, in player 5, they should all mean that there's a 5 in those two positions. So here, player 5 beat 4 and 3. So if we go and look at 1 and 2, we better see the number 5 to indicate that that happened. So if we think about how many numbers have we written down here, well, we should have written each number down, right? How many times? It should be 2 times when they got beaten. Well, if they got beaten twice, and then once for themselves. So it's going to have to do with the out degree of each vertex. Okay, but that was only half of what our list was. So this was the first half of our list. So this is written in black. We've now written these down. And now what do we want to do? We want to go through and maybe in another color, such as, for example, purple. Let's write down everyone defeated by someone that person defeated. What does that even mean? So if we think about player 1, right? Everyone defeated by someone she defeated, she being player 1. So player 1 defeated player 5, so we need to write down all the people that player 5 defeated. So that would be down here, 4 and 3. So then I'm going to write 4 and 3. And let me just take a moment to move the problem over a little bit, just to give us a little more room. Okay, so 4 and 3 is our second order of information. What about 2? So 2, we have to write down everyone player 1 defeated. That would be 5. Everyone player 4 defeated. That would be player 1. And everyone player 5 defeated. That would be 4 and 3. For player 3, we have to write down everyone 1 defeated, everyone 2 defeated, and everyone 4 defeated. Notice there's a lot of repetition in what I'm writing. That's okay. 4 is a little simpler. We just have to write down everyone player 1 defeated. And for 5, we just write down everyone that player 4 or player 3 defeated. So we write 1, 2, 4, and 1. And now the statement that we're supposed to prove down here is that someone writes down all the other numbers, okay? So here we can say, where does this happen? We have here, we've got 1 writes down 3, 4, and 5. That's not it. That does not work. We don't have everybody. Okay, what about player 2? Player 2 wrote down 1, 3, 4, and 5. So that is a success. But let's keep going. Player 3 wrote down 1, 2, 4, and 5. So player 3 is a success. Player 4, what did player 4 write down? Just 1 and 5. Player 4 is a failure. And player 5, what did player 5 write down? Player 5 wrote down 1, 2, 3, and 4. So player 5 is also a winner. Okay, so it appears to be true for this specific example that we've done, and at least now we have some concept of why this might be true, or at least how it's true. So let me give you a little definition before we delve into the proof. Here's another definition. When we have a tournament like this, a winner is any player with a maximum number of wins. Any player with the maximum number of wins. So what do I mean by that? In a tournament, right, you can win at most n-1 games. So the max number of wins is equal to, in this notation, the maximum of the out degree. Remember, we talked about the out degree of a vertex. So the maximum over all v of the out degree. For this particular example, that's 3, right? So for our example, the max is equal to 3, which means the winners there are 2 of them. Player 2 and player 3 are both winners because they have both beaten 3 people, okay? So again, winners, they're not unique in a tournament like this. It's not necessarily unique, right? And it's just whoever gets the maximum number. And it turns out that 2 and 3 satisfied the conditions. Now, 5 also did, but it's somehow less exciting to me. The real crux of it is that 2 and 3 are always going to do it. So let's write down a proof. How would we prove this statement to get us a little more comfortable with tournaments? Okay, so I'm going to let W be a winner. Be any winner. For example, it could be number 2, okay? And suppose that some player P is not on either of W's lists. Remember, W makes two lists, a black list and a purple list, okay? Then, what does that mean? That when P played W, who won? Well, P's not on W's list, so we must have had this. P beat W. So that tells us that P beat W. Okay? And what else do we know? We know that P is not on the other list. So what does the other list, the purple list, tell me about P? So that tells me that P also had to have beaten V for every V whom W beat. So what does that mean? Well, so P had to have beaten V for everybody that W beat. Otherwise, it would be on the purple list. So that means that P defeated everyone W defeated and W. So that means that P defeated more people. So P defeated one more person than W, which is a contradiction. Because remember, what's a winner? A winner is somebody who has the maximum number of wins. So this is a great example of proof by contradiction. If we suppose this didn't happen, then we arrive at a contradiction because P will have won more games than W, but we said that W won more than anyone else. And again, it's okay to have multiple winners in this scenario. I'm just saying that you couldn't have somebody who won even more games than that. And now if we think about what does this say in terms of the graph theoretic sense, this says that in a tournament, in a directed graph on Kn, the maximum distance you can be from a winner is 2. If I take any vertex that has the biggest out degree, I can get to any other vertex in at most 2 steps. That's a very important property of tournaments that we can exploit later.